What you're looking at is not only a virtual machine inside a web browser, but a browser virtual machine that lives entirely inside the URL. Yep, you heard that right. Everything you see on the screen, as well as any data that is created inside the virtual machine, exists exclusively inside the URL. You can copy it, then paste it into another browser, device, country, and you get an identical copy of the state you left it in. Well, if I managed to pique your interest, make sure to keep watching and see how I managed to create such a challenging project. Most URLs point to something: a document on a server, an image in object storage, an API endpoint, or an application that has already been deployed somewhere else. But a URL does not always have to point outward. If you write this followed by valid HTML, a browser can render that directly. There is no server behind it, no folder being loaded from disk. The URL is both the address and the payload. Of course, forget the URL and it's gone forever. You don't have the luxury of local files or cloud backups. However, on its own, in this state, I can't say this is oh so incredibly interesting. But the implications definitely are. Oh, and if you enjoy my continued suffering, consider liking and subscribing. If a URL can contain HTML, and HTML can contain CSS and JavaScript, how much of an application can the URL contain? Could it hold its user interface? Could it hold files? Could it execute background programs? Could it preserve its own state? And could the running application generate a new URL containing the updated version of itself? But let's not get ahead of ourselves. Yet. So, with that basic markup example out of the way, let's add a bit of spice to it. And by spice, I mean just ordinary web dev. And you already have the evergreen increase counter web app. There is one major difference from a typical website though. The document is not associated with a normal web origin. A page loaded from example.com has an origin built from its scheme, host, and port. That origin becomes the boundary for cookies, local storage, permissions, and same origin checks. A data URL, however, receives an opaque origin. It is a unique, isolated identity that does not behave like a normal domain. Two identical data URLs are not a shared website in the usual sense. They do not gain common storage simply because they are text matches. And if you think that sounds limiting, well, it's because it is. But that's also the fun of it, and also gives away a small spoiler towards the architecture of this project. If I can't store anything in a normal origin storage space, then the entire state of the app needs to be packaged in the URL, which brings me to the next evolutionary step of this adventure. Speaking of architecture though, not make this too confusing, I'd like to give you a short reference to what I'm looking for in the final boot sequence of this OS. This pretty much matches the iterations I'll be going through afterwards. The runtime starts inside an asynchronous immediately invoked function, and the actual, although pretty high level, boot sequence is: first, the browser parses the self-contained HTML document. Then, link.os captures the current HTML as boot HTML. Then, the embedded root file system files become base files. Next, the URL hash is inspected for saved state. That state is then decompressed when necessary. Saved state is merged with default state. Event listeners and runtime-only objects are initialized. And finally, the desktop and application windows are rendered. And gotta make sure you don't lose sight of boot HTML. It's the reusable bootloader used when the running machine exports itself again. Okay, so URL has a fragment, the part after hashtag. The fragment is available to the page, and changing it does not require sending anything to a server. So, the second important step is to serialize application state as JSON, encode it, and store it in the hash. Whenever the node changes, the application updates the hash with history.replaceState. On boot, it reads the hash, decodes the JSON, and restores the input. I should mention that what I am working towards is not a genuine OS, in case some of you were already sharpening your pitchforks. I'm not building a kernel from scratch, adding hardware virtualization, or implementing a real Linux user space. You can think of it as emulating an OS to the best of a browser's capabilities, with a desktop, terminal, text editor, file manager, process monitor, and a small browser window, all managed within a virtual file system. A conventional file system is a complex structure. It has directories, inodes, permissions, timestamps, links, binary data, and many behaviors that this project simply doesn't need. link.os uses a much smaller representation, a JavaScript object mapping absolute paths to text. This structure is useful for three reasons. First, reading an exact file is simple. Just use the path as a key. Then, the entire file system can be serialized using JSON.stringify. And third, the build system can create the same object from a normal directory on disk. Directories are inferred from path prefixes. If workspace/main.js exists, then workspace exists. Listing a directory means scanning file paths, removing the directory prefix, and grouping the first remaining path segment. Also, directories without any files obviously can't exist. So, with a virtual file system in place, the next logical step is to start doing something with it. The terminal is not a full shell. It has a tokenizer that recognizes whitespace and simple quoted arguments, followed by a dispatch table of built-in commands. Although some of these are not the actual commands as you use them on Ubuntu, for example. Nano opens a file in the editor window, whereas xdgopen opens the current path in the terminal in the file system window, which operates independently from the terminal. The prompt reads the current username, which by the way can be changed with a custom setuser command, and working directory from machine state. Command history is runtime state rather than exported machine state. You can navigate through it using the up and down arrow keys, but only in the current session. Not every value belongs in the disk image. Things like username, virtual files, shell working directory, active editor file, browser preview file are worthy to be stored as part of the machine state. A cursor pointing at the third entry in command history is only meaningful inside the current browser session. LinkOS therefore separates serializable state from live runtime objects. Also, I gotta make sure the serializable state must remain valid JSON, whereas with the runtime state no such constraints take place. But with being able to navigate through a file system, you also need to be able to interact with the files inside, aka creating, modifying and deleting them. The editor writes directly to the virtual file system object, creating a new file, selects a proposed path and opens an empty editor buffer, but it does not insert anything into the file system. The file appears only when save is pressed, and deleting it, well, just deletes the entire entry from the state.json. We also know of the existence of the iframe HTML tag, used to display a web page within a web page. And the final piece of the puzzle is the fact that iframe, aside from the source prop used to display other pages, also has a source doc prop, which allows you to pre-write HTML to be displayed inside it. Using all these three things and knowing I have the ability to dynamically edit the state, aka the URL, I can now display a browser window inside a browser window by constructing the iframe rendered HTML directly from the selected virtual file. However, all of this is running inside of a sandbox, what is rendered in the pseudo browser being completely isolated from the rest of the pseudo desktop. Maybe I should drop the pseudo part. Thus, it was time to add a controlled way of allowing processes to interact and exchange data. Thankfully, the browser, real browser. Okay, the pseudo part is still needed it seems. But nonetheless, the browser has such a means of communication. Post message. The LinkOS desktop listens for messages, checks the type, and turns the result into a notification and terminal event. Of course, this is not real IPC, but conceptually it operates exactly like one within this virtual machine. Now, up till this point, it was all fun and games. Time to get serious. Okay, I'm kidding, this took a while. A web worker is already close to the process abstraction this project needs. It has its own global execution context, communicates through messages, and can be terminated by the parent. The problem with web workers, though, is that they are deterministic. You can't just decide on the fly which code you want to run, load it into a web worker, and have it do its thing, unless your entire source code lives inside a single string that can be continuously self-edited. Workers receive a snapshot of the virtual file system rather than shared mutable access. So, to run main.js, LinkOS needs to read the source and create a small worker bootstrap. The bootstrap receives a snapshot of the file system and an emit function, and then the user program is invoked with new function. The complete worker source is placed into a blob, and the blob URL is the executable image for that worker. Each process receives a process ID and a process record containing its worker instance, blob URL, source path, state, start time, and most recent message. And thankfully to my structuring of application data in a smart way, multiple copies of the same file can run simultaneously with each process a separate execution instance. And with this, I covered creating a newborn process. But like all life, it must also end at some point. Killing a process requires more than just removing a table row. The worker must be terminated, its blob URL must be revoked, its process record must be deleted, and if no processes remain, the displayed metrics have to return to 0. At this point, link_OS can boot from a URL and store its live state in the hash. And so the next step is to make the running machine produce a new standalone URL. Early in the boot, the runtime captures the parsed HTML document as boot.html. This is the clean application image, before user files and window changes are applied. When the user exports, link_OS clones the serializable state. It clears the previous exported URL from that state, and then turns that state into JSON. If compression streams are available, that JSON is then compressed with gzip. The bytes are encoded with URL safe base64 and attached to the fragment. The application HTML itself can be represented as %encoded text or base64. link_OS creates both representations and keeps the shorter one. Now, I'd like to make a small confession. This entire time, I've been working in a single HTML file. I became so caught up in the project, I didn't even hear all the modern programming standards yelling in my ear to split it up. You've probably noticed that each blank state actually came from my singular HTML file, and the actual virtual machine URL was exported from that. That's a small caveat of not coding by typing the entire 50 kilobytes URL by hand. Of course, aside from this, all the other URLs are actually self-contained. But in my quest of splitting this project up, I decided I also wanted to be able to export the URL from the get-go. So, on to building a small compiler. The maintainable source is split into an HTML template, a style sheet, the browser runtime, and a root file system directory. The root file system is now made of ordinary files, and the compiler recursively walks the directory and creates a path to content object. It uses JSON stringify to inject that object safely into the runtime source. Then it replaces CSS and JavaScript placeholders in the HTML template. I also added some much needed optimizations. You know how I mentioned the 50 kilobyte URL? Well, originally it was over 80 kilobytes. But after removing unnecessary whitespace, blank lines, indentation and comments, compacting the root file system JSON, I managed to free up quite some space. I technically could have gone even further, but adding dependencies is almost the last thing I want to do, dethroned only by having to implement such complex tools from scratch. Oh, and for anyone interested, here's a short mapping of all the OS concepts and browser primitives I've used throughout. Now, I also want to bring attention to some things. URLs can obviously not be infinitely large. Browser behavior and copy-paste reliability would eventually impose practical limits, so can't vouch a one-to-one working copy of Ubuntu could fit inside the URL. Also, as it currently is, the file system is text-only. Binary files would need an explicit encoding and metadata format. And also, they would currently be kinda pointless. Same with coding in other languages like Python, for example. A separate compiler would either need to be added as a third-party dependency, which already complicates things quite a bit, or a new one would need to be built from scratch, which yucky. Finally, the shell is actually a command dispatcher, not real bash. It does not support pipes, redirects, globbing, or environment expansion, for example. Of course, this one is more like a mild inconvenience, because that behavior can actually be replicated, with a bit of effort, of course. But wait, there's more! Just as I was getting ready to start editing this video, it hit me. Considering the entire source code lives inside the URL, I had to add inbuilt state versioning, by adding a state version field in the state JSON, and adding validation based on that for files, Windows Terminal and other bits and pieces. And because every OS needs to come packed with its own array of games, I also added Snake. And yeah, this is how I built an entire virtual machine, packed it all into a URL, and started a new revolution against Windows.